Alright, in the last video, we talked about calculating rate of change on tables, things like that, over a specific interval, linear and exponential functions. We observed that rate of change of exponential functions change if we focused on different intervals because it's not linear, it's not a straight line, so the rate of change is not going to be constant. Here we'll focus on graphs of linear and exponential and learn how to estimate rates of change. Okay. Alright, so key concepts, make sure you read through those. We'll be using the slope formula to do this between 2 points. So make sure you identify x1, y1, and x2, y2, starting and ending points. And this is average rate of change. It's not going to be a perfect rate of change unless it's a linear function, like this first example here. So we need to find our starting and ending points. So it looks like our starting point is here. All right, so that would be 0, 1.5, and it looks like our ending point is down here, which looks to be 155, 0. Okay. All right. So make sure you understand the context of this problem. We have the fuel remaining in your tank as the y, and we have the distance traveled in miles. Okay. So if we calculate our rate of change, we're going to do y2, which would be 0. Minus y1, which is 1.5, over x2, which is 155 minus 0. So I get negative 1.5 divided by 155. Okay? And when you divide that out, you get negative 0.0096. So we're going to round that. So that is approximately negative 0.01. Okay? Which means what? You are losing you're losing 0.01 gallons for every mile. Okay, or per mile. Alright, so again, that's just taking 2 points on the graph and averaging the rate of change. Find the average change between them. Okay? Alright, so the next one, and the reason I noticed it's negative here, I didn't put a negative down here because I used the word losing, which implies that we're going downhill, it implies that negative 4. Okay? Just make sure you understand the difference between those things. You could also say the rate of change, or the amount of gas left is changing at a rate of negative 1.01 gallons per mile traveled. You can do it that way too. Alright, next, Jasper's invested an amount of money into a savings account. Below the graph shows the value of investment over a period of time. What is the rate of change for 1, 3, the interval 1 to 3? So I'm looking when x is 1 and when x is 3. Alright, so I can go ahead and do this. 1 comma something. 3 comma something. It's my 2 points. So at 1, I am right here. I'm not at 600, but I'm well above the halfway point. Looks like I may be at about 3/4 of the way. Anyway, we'll go with that. We'll call it 550. And then at 3, which is the other point, looks like I am here, which again we need to call something. So let's go with, I don't know, maybe 1100. Pretty close. That had to be perfect here because, and if I give you one like this on a test, I'll make sure you're calculating your average rate of change at nice, neat, what they call lattice points. Points like this. This is the lattice point where two grid lines come together. I'm not going to try and get you to estimate too hard on this kind of stuff, but it's good to know how for the examples. And if you do have one like this in the Walsh practice, just estimate it, guys. If you're within reason, I'll give you credit. It's not a huge deal as long as your work is there to back it up. All right, so once you have those 2 points, when we calculate the average rate of change, that's 1100. Okay, remember this is x1, y1, x2, y2. Make sure you've read the notes. I'm kind of skipping over some of the instructional part of this and just showing you how to work these examples. Make sure you're reading. So y2 minus y1 over x2 minus x1, which is 3 minus 1. Again, it's just slope formula, okay? And when you do that, when you subtract that out, you're going to get 550 over 2, which means your rate of change is 275, okay? 275. So what does that mean? It means the rate of change for this function is approximately $275 per year. Okay, so $275 per year. Now, let's do the same problem, and I'll go ahead and go to example 3, and then I'll come back. Jasper is curious about the rate from 3 to 6. So I'm going to go back over here and do my work for example 3. So what if instead it was 3 and 6? Well, 3 we already know was 1100. And at 6, it looks like it would appear to be, let's see, scroll down a little bit here. 6, maybe here. We'll call that 3100, just to be nice with my numbers here. So that's 3100 minus 1100 over 6 minus 3, which is a nice even 2000. Divided by 3, which doesn't work out to such a nice neat whole number, but you get 666 repeating, whatnot. So what we'll do is we'll just round that to $666.67 because again that 6 was repeating. So we're talking about money. So that's dollars per year. So per year. What I want you to notice is because it's a curve, that interval, right? That interval is much steeper. Right, the further on you go in an exponential, the rate of change changes. There's a variable rate of change, not constant. All right, so that's how you would do it from a graph, guys. So good luck with 332 and 333.